Good to go.
Yeah. So I welcome you all once again for the second lecture of the day. I'd like to thank each and everyone present with us for your continued support and participation. The keynote speaker of today's lecture is Dr. David Wald from United States Geological Survey. He's having an early start to the day to compensate for the time difference, for which I'm very much thankful to him. The title of his today's talk is an overview of USGS near real-time earthquake information products. But before his talk, may I request our session chairman, Professor J.R. Kyle, to say a few words. Over to Professor J.R. Kyle.
Thank you, Shantanu. Thank you so much. David, it's so nice to see you on the screen. And we welcome you all to this platform. And we are really, as Saurabh said, we are really lucky to have you this evening. Rather, we make you to wake up in the early morning. So we look forward to listening to you, your lecture, your sharing of your experience with our participants. So Shantanu, please. Over to Shantanu.
Thank you so much, sir. Now let me read out a short biography of Dr. David Wald. He is involved in the research, development, and operations of several real-time earthquake information systems at the USGS National Earthquake Information Center. He developed and manages ShakeMap, TwoPager, and is responsible for developing other systems for post-earthquake response and pre-earthquake mitigation, including ShakeCast and TwoPager. After pursuing MS in geophysics from the University of Arizona in 1986, Dr. Wald completed his PhD from California Institute of Technology in 1993. He also carried out postdoctoral research at the National Research Council, USGS, Pasadena in 1995. He has advised dozens of postdoctoral, graduate, and undergraduate student research projects from the Caltech and Colorado School of Mines. Dr. Wald's diverse research interest has resulted in more than 450 professional publications. I conclude here and request Dr. Wald to take the digital space and enlighten us with your lecture. Thank you. Over to Dr. Wald.
Good morning, good evening to you, and I will be sharing my screen now. How does that look?
It looks very
perfect.
Okay, excellent. Well, thank you so much for the opportunity to be here. I'm quite honored, and I'd be glad to share with you an overview of the USGS real-time earthquake information systems, that, in particular, the ones that I've been heavily involved with developing. And I speak to you from Colorado in the United States, and this is a picture of the National Earthquake Information Center, the NEIC, and it's where we respond to earthquakes both domestically and around the globe. Before I get started, since I don't have the opportunity to be in person with you and meet everyone, I just wanted to share a small tidbit about my own personal life rather than show you that all is about work. Work and play is a good, important mix. And so here's a picture of my burro, donkey. His name is Mickey. And unique to Colorado is something called burro racing, or pack burro racing, where you run 10 kilometers up to somewhere, sometimes up to 50 kilometers with your burro and race against other teams. So life is not all work. There's always fun things to do, and I just wanted to distract you from seismology for 1 minute. But alas, back to seismology. Rapid earthquake shaking impact estimation for global earthquake response is the primary role of my team, and today I'll give you an update and an overview of USGS earthquake information products, including some new ones that we're developing on ground failure and other avenues. I'll also take you down a path of some new directions that we're heading, that we're currently working on in terms of updating these models based on imagery and ground truth information that comes in after a significant disaster. During the we'll also have time obviously for discussion and questions and answers, but during these topics I will be describing the range of users and uses of each product, as well as the underlying scientific challenges and communication issues that we have for each system. Now, I don't do this on my own. We have quite a nice team of colleagues here at the USGS working on these real-time products, and these are the folks in particular. Many of you may know Dr. Kishore Jaswal, who he went to IIT Bombay for his PhD and worked for RMS for a little bit. And now he's working with us at the US Geological Survey as a structural engineer, leading our loss modeling effort. But we also collaborate with external researchers, and here's a few of the people that we've been working with. Basically, we fund external academics and contractors and consultants to help us with work when we need to cover challenging areas that they're experts in. And so we support both our internal efforts as well as colleagues working in the academic world to help us with our development. Well, the motivation behind what we're doing is such that they're very devastating earthquakes around the globe. There's many earthquakes every year, but only a few of them turn out to be deadly or devastating, like the magnitude 7 Wenchuan earthquake in China in 2008. This earthquake, as you can see around, there's landslides have denuded the hill slopes. The fault went right through the city of Bechuan, and the buildings are heavily damaged here. This is Kishore and Nico Luco, also an engineer in our group, and Dina Diala, who's a structural engineer at Imperial College London, University College London, doing reconnaissance after this earthquake. And here's myself and Nico Luco trying to understand the situation as best we can. This motivates a challenge that we have here at the National Earthquake Information Center, and that is to determine which earthquakes are going to be unimportant in terms of societal consequences, the green dots here, which ones are going to be local disasters, yellow, national disasters, orange, or international disasters, red. And these are done with what we call the TwoPager system, which is the prompt assessment of global earthquake for response. We're going to talk more about this, but effectively, we really need to know, and our users need to know, if an earthquake of magnitude 5, 6, 7 is of significance, and that's a determination of whether it's in a populated area and whether that area is vulnerable to damage from earthquakes. So the beginning of this process is at the NEIC is to monitor seismic data and seismic stations around the globe. We have thousands of seismic stations coming into our basement, and so we are considered national critical infrastructure in that we get very important data coming into our basement, where we monitor that, we respond, but we also do the research that's involved with getting the new products and new information tools out to users so that we can improve the content of the information we provide. So we're no longer just providing magnitude and epicenter for earthquakes. About 20 years ago, that's about what we were doing in the minutes and hours following an earthquake. But over time, in the last 20 years, we've evolved from just the magnitude and location to maps of the intensity distribution of shaking around the epicenter, around the causative fault. And then further, we turn that into notifications and feeds. And then we've been able to turn that shaking estimate into estimates of damage at particular facilities, an estimate to damage to the entire population, as well as now, as I'll show you, determine whether they're likely to be landslides and liquefaction, and even the number of buildings that may have been in fact impacted. So things have evolved very quickly over time, and they continue to evolve. And now what we have is what I like to refer to as the USGS Earthquake Information System. And the way I think about it is, what tools do we have in the pre-earthquake planning environment? Which earthquake tools do we have that are at the time of the earthquake, and then post-earthquake information for response and recovery? And so this is a suite of tools, and I won't be going through all of these tools, but I'll be focusing on several of them. In the pre-earthquake planning environment, we have probabilistic seismic hazard maps for design and for insurance purposes. And from those, we can develop scenarios, and the scenarios represent particular faults inside the probabilistic seismic hazard map that may rupture. We can look at a shake map of those and make that into a planning exercise. But what I'll focus on primarily is the actual post-earthquake tools. Now, one of the things to note is that these tools are very dependent on each other. When we get a magnitude location within a few minutes of an earthquake, that triggers a shake map. The shake map is the depiction of the shaking intensity in map view. And then as soon as the shake map's available, we send that to the pager system to assess the losses. We also send it to our ground failure system to estimate what the land size and liquefaction are likely to be. And these tools, again, are connected. We need to get the finite fault in order to estimate what the shaking is. And the Did You Feel It data, as you see, can also contribute to the shake map, as I'll show you in a minute. So there's a dependency here that requires us to have a lot of these tools in-house in order to have these triggers of a product and an adjacent product to provide more information comprehensively. So what I'll do today right now is focus on these 4 earthquake information tools, and these are the pager system, the ShakeCast system, the Did You Feel It, and the ShakeMap system. So on the lower left, the Did You Feel It system is effectively a citizen science tool. You may have used it, you may have seen it. And basically we ask questions of the recipients of what they experienced during an earthquake with a short questionnaire. And we tend to get thousands, even tens of thousands of responses. In this case, we had 142,000 responses for a magnitude 5.8 earthquake in the central and eastern US. We also have the ShakeMap system, which is independent, but it uses the seismic stations in the ground to determine the shaking level and then interpolates the shaking level to get contours and a depiction of the intensity of shaking. The key is that these tools then are dependent on each other. So Did You Feel It is often very useful where we don't have enough seismic stations in the ground to get a good depiction of the shaking. As I mentioned, as soon as the shake map's ready, that goes to 2 different systems. One is the pager system that I mentioned, and that's again the prompt assessment of global earthquakes for response. And that gives us the estimate of fatalities and an estimate of economic losses for that particular earthquake in that region. In this case, there's an orange alert for economic losses, which gives us the total alert, and a very low likelihood of fatalities because of the nature of the construction and the nature of the shaking. At the same time, ShakeMap is available to other users that are distributed around the country and around the world that run a system called ShakeCast. And ShakeCast takes the ShakeMap and allows people to look at particular facilities and to determine whether those facilities are shaken to a level that would cause concern. And it generates reports automatically that tells them which structures need to be inspected. So effectively, the Did You Feel It system is a citizen science tool. It allows the citizens to report what they experienced. ShakeMap is more of a geospatial tool and a seismological tool. And then both the pager system and the ShakeCast system are effectively databases that have engineering information that allow us to turn the shaking estimates into loss estimates. As I mentioned, a number of these tools are used by a wide variety of users, and these are acronyms or logos of a number of different groups. There's many other users, but these logos provide us with the motivation here. There's a lot of different users that make different decisions, some of them financial decisions, whether to send aid, some of them are emergency response decisions, others are making decisions about whether to get out of bed or whether to get to work for a particular earthquake in their location. There's businesses, there's different federal agencies and international agencies that need to make decisions. So we have a pretty wide audience, and interacting with these groups gives us the motivation and the desire to get the products right and to produce different flavors of products that can be used by different types of users and different sophistication of users. One of the obviously primary groups is the media, and so a number of our products are used by the local and international media for earthquake response. The picture in the lower left is one of my favorites. This is Governor Schwarzenegger when he was governor of California, trying to describe what a shake map looks like in Los Angeles. But obviously these things get used and redistributed widely through the news media. So let's look at how this works. We call this our event page, our earthquake event page. This page gets made on the fly, completely new, as a significant earthquake occurs. And you might have just heard a text message. There's a magnitude 6.4 earthquake off Chile just a few minutes ago. So that will generate its own web page. But this is something that happened back in 2020, and this is an earthquake of magnitude 5.7 in an urban area of Utah, close to Salt Lake City. As the magnitude and location get built and the other products get generated, they each show up as these cards on the event page. And there's a variety of different flavors of products that will show up, and they're not all here for all earthquakes. They have to be important to that particular earthquake. But one of the pages I like to go to is the interactive map, and I usually start with that map, and I'm going to zoom in on that map. And that map gives us a lot of information. So right now I'm looking at the contours of seismic intensity, and the color coding is here for the intensity scale. And these are contours of shaking intensity, and they're contouring the seismic stations and interpolating between the seismic stations. The seismic stations are also color coded according to intensity. And you can see that the pattern of shaking is close to Salt Lake City. But with this map, I can add all sorts of different layers and help to kind of interpret what's going on for this earthquake. I'm going to add the population layer. Now, this is the urban corridor of Salt Lake City along the mountain front of the Wasatch Mountains in Salt Lake City, Utah. You could see that the strongest shaking missed the highest population area, so this won't be that large a disaster. And also the contours here are of intensity 7, maybe 7.5, so it's not the highest shaking intensity, and that's because this is a magnitude 5.7 and not a larger earthquake. The other thing I can add here now is the Did You Feel It data. These are 1 kilometer cells color coded to the average response of different internet users to the questionnaires that we put out, and these allow us to compare the same intensity scale, the seismic stations, with what was experienced by the people that felt the earthquake. And you can see the great correspondence between the population and the Did You Feel It responses. So whether or not we have seismic stations, we can get a lot more information where people experience the earthquake from the Did You Feel It system, and combining these, we get a more robust map of the shaking intensity. And one of the key features about the ShakeMap is that we take what we record in the ground, which is the peak acceleration, and we can convert that to this color-coded intensity and estimate what people will experience. But we can also take what people experience and estimate the seismic intensity and the peak acceleration. So that allows us to combine these two disparate data sets into a single map and have a more robust depiction of the shaking intensity, whether or not we have lots of seismic stations in the ground. So we've developed this scale to allow us to convert from user experience, the intensity, to what we record in the ground and back and forth. The latest thing that we're able to do now with the ShakeMap is to pass that through to models that allow us to depict ground failure. And you can see the color coding of the ground failure here is green and yellow, which means there's very low levels of likely landslides and liquefaction. And that comes from analysis of both the aerial extent of landslides and whether or not there's population exposures to them. So I won't go into great detail here, but this would go up higher and higher if there were more landslides probable and the landslides correspond with the population. That would give us yellow, orange, and potentially even red alerts. So for this particular earthquake, again, a moderate size, what did occur in a very flat-lying, low-lying area next to Salt Lake. And so these are moist soils here, and the probability of landslide was not high, but moderate. And the landslide probability, or sorry, the liquefaction probability here is shown on the scale. So there were some areas of liquefaction in the areas indicated, and so that was fairly successful in terms of the distribution of potential liquefaction. This is the landslide map, and there's no landslides probable, and that's because the shaking ends right where the mountains start. If there was strong shaking within the mountains, we'd expect to have very significant landslides in the mountainous areas. So this again is very useful. The other thing I can do is take the Did You Feel It data and turn that into a movie. And so these are 10-second snapshots of the reports that came in. We ultimately received about 25,000 Did you feel it reports. What's interesting about these reports is if you let these repeat here, you'll see that the epicentral area received the reports later than the areas in the outlying areas. We can actually look at that in more detail after 5 minutes, 10 minutes, 30 minutes, and the final Did You Feel It map. What we see, and we've seen this again and again, is there are what we call a donut hole. There's a hole where there's very few reports initially in the epicentral area. And that's in part because there was power lost in the epicentral area. And also people that feel very strong shaking are not immediately going to get on their computer and respond to the Did You Feel It questionnaire. And we've seen that over and over again, and we're worried that if the power is out and the internet is out and cell phone coverage is out, that we won't get responses. So we've actually got help from what we have is amateur radio or ham radio operators around the world. This is a house in Los Angeles with a large antenna, and this antenna is for independent communications from the network and from the utilities. And this is a ham operator, amateur radio operator. And we worked with a gentleman, Oliver Dully, to develop a questionnaire for ham radio operators. All they need to do is go down and select the USGS form, and that allows them to fill out the Did You Feel It questionnaire and send it through their alternative communication means. And they actually have a means of sending email via radio, and they can do that even without power and even without internet or any cell phone coverage. So this allows them to provide a emergency service during earthquake disasters. And these amateur radio operators help out around the world when there's a disaster to help communicate, to help hospitals communicate and others. And so they're very well suited to help with this particular problem. And this is an article that we published in EOS to show how this helps fill the donut holes in case of a loss of power and communication. Now let's just go back to that Utah earthquake near Salt Lake City. This is the one-page result, the pager results for that particular earthquake. And again, there was a high probability of damage in the $100 million range of damage. And in fact, that's the type of losses that happened due to building damage. There were no fatalities, and the pager estimated that there would be no fatalities. But this is a very successful tool to estimate the overall impact in human and economic terms. We've actually developed a new tool that's working only in the United States, but we hope to bring to the rest of the world. We call that the TwoPager. And with enough information about the inventory of structures and their vulnerabilities, we can go beyond just providing the overall estimate of economic and fatalities to provide estimates of the building damage. And so this green, yellow, and red tagging is the nature of inspections that would be needed for this earthquake in terms of buildings that are safe to live in, restricted use, and unsafe if they're damaged. And that now allows us to develop county level or regional level estimates of losses and not just the overall losses. And so this is something that we do within an hour or two of an earthquake in the United States. Now the Did You Feel It system is quite widely used, and it allows us to do some really interesting things. One is to compare earthquakes in the eastern and western United States. Similar to India, where the continental earthquakes are in a stable shield and result in much stronger ground motions than those in the active tectonic areas. For the same size earthquake, magnitude 5.8 in the east and a magnitude 6 even larger in the west, you can see that the felt reports and the intensities are much wider in the central and eastern United States. We've seen this over and over again, and the reason is, like in India, the eastern part of the United States is stable shield, and it absorbs energy a lot less than the active tectonic areas of California. So just from the human reports here, we can see how wave propagation is much, much less attenuated in the east than it is in the west. And over time, we can collect information about earthquakes all over the country. This is just 1 year of earthquakes. And what we've noticed in the last decade is a very active part of the central United States that's due to induced seismicity due to petroleum extraction and the injection of fluids back into the ground. That's 1 year. Here's what we have for the last 20 years of felt reports. And this now is starting to reflect a longer time period of earthquakes. And as such, it actually looks now quite similar to what we have for the probabilistic seismic hazard map. So this is our long-term estimate of hazards in the United States. And this is what we're seeing in a 20-year period. And they're starting to look similar. Although you'll notice that the large areas of expected shaking that haven't ruptured, like the Cascadia subduction zone, large earthquakes in the Wasatch Front and other areas. But again, we're starting to see that over a long time period that we're reflecting the long-term hazard. And I can also look at the entire collection of felt reports, over 6 million for earthquakes around the globe. And we can zoom in and see that, primarily we're getting many, many responses from the United States, but Europe and Asia, in particular the Himalayan earthquakes that have happened in the past, South Africa and South America reporting, as New Zealand and Australia. So we're starting to see a very wide range of users of the DigiFeel system. One can convert the questionnaire into different languages, and so this is very helpful in getting users around the world to respond appropriately in their location. The other thing we do with the DigiFeel data is to evaluate how people respond to earthquakes. They often provide first-person accounts of what they did after an earthquake or during an earthquake, and that information allows us to improve the other tools that we use by understanding how people tend to respond to earthquakes. And so there's a number of different efforts to analyze DigiFeel data from social scientists to understand how to better make our seismological tools work for people. With the ShakeMap, that system software is freely available and it's distributed through GitHub. And we have a number of different countries around the world that are running ShakeMap. In addition to our own system, we call Global ShakeMap GSM. So we make a ShakeMap for any magnitude 5.5 earthquake or larger around the world, but other countries have their own seismic networks and are running ShakeMap and distributing that internally to their users and their population. So we have a very nice collaborative effort with a number of different countries where we are developing the software and providing updates to many users around the globe. We also have what we call a ShakeMap Atlas, and this is now 120 years of earthquakes where we have done our best to take the historical information from each of the earthquakes, whether it's ground motions or whether it's macroseismic data. Remember, we can combine historical macroseismic data with seismic instrument data to make a better shake map. And so this is over 14,000 shake maps around the globe, and each one of these is made up of individual shake map prints. And we've taken the largest intensity, the highest intensity at each location to make effectively a hazard map for the entire world. The important part of this is that we can now take any location and effectively we can make a hazard curve. These are the number of different, over that time period, the occurrences of certain earthquakes and their intensity. And effectively, we can turn that into a hazard curve, which tells us how often a particular location has shaken historically. And this is something we compare to the probabilistic seismic hazard map. This atlas of earthquakes, as I mentioned, 14,000 earthquakes, is available online, and one can just put in the year or search by map and find earthquakes of that particular location and time period. And it goes way back in time, as I mentioned. This is the shake map for the 1906 Great San Francisco earthquake, magnitude 7.8. And we actually have nearly 1,000 intensity reports of the historical accounting of what's happened. The black line here is the fault that ruptured. And so this shake map is as good as a modern shake map. It doesn't have the instrumental data, but the intensities are very, very well reported, and the fault is well known. So this shake map is extremely useful for calibrating against losses in historical earthquakes and what's happened in terms of landslides and liquefaction and other impacts of that earthquake. Now, with ShakeMap, it's gotten to the point where it's used after the earthquake for very important decisions. And over the last 10 years, there's a number of financial decision-making tools that have been developed. Large insurance and reinsurance companies are using ShakeMap to determine payouts for insurance and reinsurance. These are called cat bonds typically, and they are triggered by not the actual losses in the earthquake, but the projected losses or the shaking estimates. So they're called parametric triggers, and they're determined by the information that the USGS puts out. So the information that we put out has to be very detailed, and there has to be a very important paper trail and accounting of what we did. And then we've had situations where for Mexico, for Haiti, for other earthquakes, there have been hundreds of millions of dollars of insurance products triggered by the ShakeMap itself. And so just recently we published a paper that details the ShakeMap operations, policies, and procedures, because the maps change with time immediately after the earthquake. As more data come in, we can update the maps. As more information about the magnitude and location in the fault, we can update the ShakeMaps. And our users need to know exactly what's happening and where to get information about those changes. Now I'm going to move off to another system called ShakeCast. I mentioned this earlier. ShakeCast is a system where we develop the software, and it's open source software, again, available through GitHub. We provide that software to critical users. And what the users do is to take the software and it allows them to automatically retrieve a ShakeMap in their region of interest. It then compares the shaking to the fragilities of each of the facilities that they have, so to determine whether they're likely to be damaged. And then it sends this one-page notification and other products to the users and to specific users depending on the nature of the outcome. And it's meant to raise the situational awareness in the immediate minutes and hours and even a few hours after an earthquake, before the ground truth information comes in. So on the right is the report that gets put out. This is for an earthquake, that same 5.7 earthquake in Utah. This is the ShakeCast report for the state of Utah Department of Transportation, and they're interested in whether their bridges are damaged. And so this map shows the bridges on the footprint of the ShakeMap and the likelihood of damage, or what they call the inspection priority. And the inspection priority allows them to determine which of the thousands of bridges that they have need to be inspected. There's just too many bridges to inspect, and so they need to prioritize. So for that particular earthquake, there are a number of different groups that are running ShakeCast. This is the Highway Administration for the United States, the Department of Veterans Affairs, which has hospitals, and they're concerned about hospitals in the area. FERC, Federal Energy Regulatory Commission, is worried about dams where there's power generation, and so they get alert with information about dams and so on and so forth. And so there's a number of different users that use ShakeCast for critical decision making and inspections. And we've got some logos here of different groups around the world and around the country, and they include critical facilities, a lot of lifelines and utilities, whether they're pipelines or waterways or different electric transmission systems. There's also a lot of agencies that use ShakeCast with their facilities. Businesses are very interested in post-earthquake recovery, and so on and so forth. So we have a number of different users. The important thing about ShakeCast, though, is one needs to know what you have in the ground and how it will respond to earthquakes. So this is just a typical example of the type of fragility that needs to be used for each facility that's in the ground. So for a Department of Transportation, this is a bridge fragility for a particular bridge where they take the ShakeMap shaking level, in this case the spectral acceleration, and based on the shaking acceleration, they can determine the likelihood of being in green, yellow, orange, and red damage states. And those damage states then get turned into this alert, and the color coding is based on the potential damage state for that particular earthquake. This is a different earthquake in a different region. This is Idaho, magnitude 6.5, but fairly remote area, so there were a few bridges. But in general, that report provides a lot of information about the inspection priority, the distance to the epicenter, the acceleration, velocity, and spectral acceleration, intensity, and other information that the user wants on that report. And along with this report, they also get spreadsheets that they can bring into Excel, or they can also bring in KMLs they can bring into their GIS systems. Here's a particular user's example of why ShakeCast is important. A lot of utilities, and a lot of utilities still do this, they'll draw a circle around a map. This is a magnitude 6 earthquake north of San Francisco. This is Napa Valley, wine country. And there was a magnitude 6 earthquake there back in 2014. And normally the utility would draw a large circle at a particular diameter based on the magnitude and inspect all of the facilities, in this case, all of the dams, within that diameter. And that's hugely costly if it's unnecessary. With this ShakeCast system, they would only need to inspect the yellow, orange, and red facilities in the epicentral area and in the areas that shook the hardest. The color coding here, the gray here, is the areas that shook the hardest. And so this allows them to inspect much more focused and not waste their time on facilities that aren't likely to be damaged. Now that's just a small earthquake, magnitude 6. If for a scenario, a magnitude 7.8 on the San Andreas Fault in Southern California, that inspection priority that a lot of utilities still use to draw a circle around the epicenter would really be misleading. They would be inspecting everything, all the dams in this area, whereas the fault ruptured in our scenario here and the strongest shaking along the fault and within the Los Angeles basin would lead them to have to inspect many, many more bridges along the fault. And so this is the beauty of the ShakeCast system. It takes the shake map and it overlays their facilities and determines what structures are likely to be affected. In particular, which ones that are most vulnerable that will be shaken will need inspection. This idea about the fault dimension being very important in the shaking, I'll amplify that. Here's a magnitude 6, 7, and 8 earthquake. These maps are roughly on the same scale. These are shake maps of the acceleration of the ground. We can actually look at the intensity of the ground, but the black line here is that same earthquake I just showed you, the Napa Valley earthquake, magnitude 6. The fault is right in here and it's only about 15 to 20 kilometers long. For a magnitude 7 earthquake, the fault gets to be tens of kilometers long. And then for a magnitude 8 earthquake, we're looking at hundreds of kilometers of fault length. And the shaking is going to be most intense along the fault length. So as you get to a larger earthquake, you're getting to a larger fault that's going to have shaking over a larger region. And it's very important to either have enough sensors to monitor that fault or to quickly determine which fault ruptured during that earthquake. This rupture could have easily gone along the Denali Fault to the west, in which case the shaking pattern would be very different. So at the NEIC, at the National Earthquake Information Center, one of the systems that we have is to determine this fault dimension as quickly as possible and to input that into the shake map to better estimate the shaking. That typically takes us an hour or two for a simple earthquake, or a little bit longer for earthquakes that are more complicated or slightly smaller that are hard to evaluate. So again, that fault dimension, as I mentioned for the 1906 earthquake, is really what's driving the strongest shaking along the fault, and so it's very important to establish that. So let's move over to now the pager system. So as I mentioned, the pager system gives us the estimate of fatalities and economic losses. How does it do that? Well, with the ShakeMap Atlas, which is now goes back even further in time, we have thousands of shake maps from historical earthquakes. We estimate the population at the time of the earthquake, and we know what the economic and fatalities are reported for each earthquake. So for each country, we can derive a formula for the fatality rate as a function of the seismic intensity from the shake map. And these vary from country to country significantly, and we're going to zoom in on that. These vary very significantly. In fact, they vary almost 4 orders of magnitude between California and New Zealand, where there's very, very strict modern buildings and modern engineering codes, to say Iran, where there's very, very heavy informal construction, and particularly in masonry and adobe, that are very heavy and very deadly. And so at the highest intensity in some countries, you're going to get much higher fatality rates than you would in areas that are well engineered. And this is based purely on what's happened in the past. What earthquakes caused what fatalities at what intensity levels with what population. So we've done this for countries around the world, and this now can be used for any earthquake going forward, where if we have an earthquake in Nepal, we can take that curve and estimate the population exposed to each shaking level and estimate the fatalities. So we do that, and this is, again, what it looks like for the globe for the 10 years that we've been doing this. And these color codings, again, are the fatalities and economic losses that we estimate for each earthquake. And that works automatically within about 10 to 15 minutes of the earthquakes around the globe. And this is the key to the pager system. This alerting is developed to be two things. One is we never provide the actual estimate in terms of numbers of fatalities. We only provide ranges of fatalities. And yellow coding is between 1 and 100 fatalities. So the median estimate is in this box, and we turn the alert, we turn the alert to that median value. But one can look at the histogram and get a sense that it's very uncertain, and we can give an estimate of the likelihood of being in adjacent ranges of fatalities. The uncertainty derives from the fact that the ShakeMap is uncertain, the population that we have estimates of is uncertain, and the vulnerability of that particular location, the buildings and the nature of the construction is also uncertain. So we'll never have an exact estimate of, we'll never be right exactly, and so we give a histogram of the range of fatalities. We also give a histogram of the range of economic losses. It looks quite similar, where a red alert would be an estimate of $1 billion worth of losses. And in some situations, we have very expensive earthquakes with few fatalities, and sometimes we have very, very high fatalities, and these demand different types of responses. So going back to that Utah earthquake, and you can now see that these histograms give us an assessment of where the median value is, and also where the uncertainty is in terms of our economic and fatality estimates. For earthquakes around the globe, where there are more vulnerable structures and larger earthquakes, we can have very significant fatalities and economic losses. And this is the kind of reports that we put out for Japan and Ecuador. And the information in here is very useful. The population exposed at each intensity level is what we use to determine the number of fatalities and the economic losses, given the intensity level and the population exposed. So this is very important. We also give an estimate of the economic losses in terms of the GDP, the gross domestic product of each country, because that will decide whether or not the country is going to need international aid to recover. And we also have information about the structures, their vulnerability, and the predominant types of construction types. We also have the cities that are nearby and the shaking intensity and the population, as well as information about historic earthquakes in the location. On the, sorry, I'm getting ahead here. On the user side of this, Pager has a variety of different types of users, and these users are typically humanitarian aid, response, government response, but also, as I mentioned, financial decision makers and risk analysis who are giving advice to other financial users. And then there's the media, of course, who are very interested in the overall nature of earthquakes around the globe. INSARAG is actually a group that is the International Consortium of Urban Search and Rescue Teams. And so they have to decide whether to send search and rescue teams internationally in the case of a major disaster. Now, moving on to an important factor is that Pager is driven by ShakeMap. Pager does not have an estimate of landslides and liquefaction that may cause additional losses. So the pager results are currently only providing shaking estimates of damage. For that earthquake in China that I started with the photos, the number of landslides were in the hundreds of thousands, and the landslides contributed greatly to the losses. There were 88,000 fatalities, 20,000 of which were killed by landslides. And you can imagine why, because the slopes all around the urban areas were completely denuded from the strong shaking and caused additional problems. So one of the things we're trying to do is to evaluate from the shaking map what the likelihood is of landslides and where those landslides will occur. So we have the same problem domestically. We haven't had a very major earthquake in the United States, but the 1906 earthquake had liquefaction all throughout San Francisco and landslides all throughout the surrounding region. And such an earthquake would cause not only shaking damage, but additional damage due to landslides and liquefaction. So we've developed a model working with our external collaborators that takes a variety of different layers that give us a landslide susceptibility, and they include this topographic slope, the soil moisture, the soil strength, the shaking estimates, whether it's acceleration or velocity of the ground, and also the shear velocity of the shallow soil. And we calibrated this model with a logistic regression by looking at all of these hundreds of ShakeMap historical events from the ShakeMap Atlas for which there were landslides. So we can calibrate a landslide model based on historical earthquakes with all those examples of historical shaking maps. So when we have earthquakes now, and this is a 2018 earthquake, magnitude 7.5 in Papua New Guinea, here's a situation where we got the alert levels for ground failure are both red for landslide and liquefaction. And the reason is that we had very strong shaking that reached the mountain front and had very strong shaking in the steep slopes. And so our probabilities here are relatively high for the region. And what actually transpired were some very devastating landslides that not only affected the population, but affected response and recovery, and really damaged a lot of infrastructure, and particularly oil infrastructure, where a lot of the economy depended. So this ability to project what happens in landslides is very important. Another thing that we do with the ShakeMap and Pager system is we develop scenarios for potential earthquakes that come out of the National Seismic Hazard Map. So a lot of users want to do drills and exercises of what if situations for earthquakes in their area and plan accordingly. So we've developed tools to use the ShakeMap system to input a fault model and estimate the shaking for different magnitude earthquakes. And we've done that for now hundreds of earthquakes around the United States and around the world that allow people to use the ShakeMap to generate a pager alert and even a ShakeCast alert for that particular scenario. So after that magnitude 5.7 earthquake in Salt Lake City, they were worried about what might come next. And we were able to say, well, if there's a larger earthquake, here's the kind of shaking and here's the kind of impact to your infrastructure that you'll have to face. And so these scenarios are then used for drills and exercises and planning purposes for communities that are and utilities and agencies that are concerned about earthquakes. In fact, we can do the same thing for that 1906 earthquake. We can actually run that as if it occurred today and get an estimate of the economic losses and the fatalities, as well as the TwoPager, which gives us an estimate of the number of buildings that are going to be affected by that earthquake had it occurred in modern times. I've added this slide. We've done the same exercise for some of the historical earthquakes along the Himalayan front, and as well as scenarios for gaps that may exist. And so we can make shake maps for any of these earthquakes with the predictive tools that are in ShakeMap. These are highly uncertain because the ground motion prediction equations are not as well established because of the lack of data in this region. But we can then take these scenarios and actually compare those to some historical earthquakes where we have intensity data and make an assessment of how accurate we could be if we know where the fault is that ruptured and how reasonable can we recover the estimated intensities as a function of distance for these earthquakes and get some sense of confidence in our ability to estimate shaking from future earthquakes. And in fact, we've done that for In 2013, we generated a scenario of magnitude 8.1 for the State Department, the Office of Foreign Disaster Assistance, to understand what kind of aid Nepal might need for this kind of earthquake. And we estimated 20,000 fatalities and $10 billion worth of losses. And then it turns out 2 years later, we had an actual earthquake that was fairly similar in size and dimension, with very similar losses, slightly smaller because the magnitude that actually happened was smaller than our scenario. So you could see how these tools that are developed for response can also be used for planning purposes through the scenario process. And we can look at historical Atlas earthquakes and get a sense of what's happened in the past and what would happen in the future if we had similar earthquakes. Now, the last thing I'm going to spend a few minutes on is our ability to improve these models with time. One of the challenges, as I mentioned, is the ShakeMap system provides estimates of shaking. They're uncertain. If we had seismic stations everywhere on the ground, everywhere on the planet, we would know what the shaking is, but we don't. And so the ShakeMap's uncertain. Our estimates of the population are uncertain, and our knowledge of the building structures and the vulnerabilities are uncertain. So our pager system is always going to have a sense of uncertainty inherent to it. What we're trying to do now is to rapidly turn our estimates of fatalities and economic losses into more accurate estimates based on evidence that we have after the earthquake that come in from satellites and that come in from reports on the ground about actual occurrences of fatalities, liquefaction, building damage, and landsliding. And so this is a nice cartoon. My good friend David Lallemant at Singapore drew this cartoon. And basically you have a prior model, and in a Bayesian kind of updating strategy, one can increase the accuracy of the model in terms of getting close to the ground truth and decrease the uncertainty of the model. If you start bringing in prior evidence to the prior model, have a posterior belief, new evidence will then give you more and more accurate solutions with time. And so that's what our philosophy is here. And as I showed you, we have a number of dependencies in this earthquake information system. And if we just look at the notion of our current approach, is that we get a magnitude and location, we make a ShakeMap, we make a pager result. If the magnitude and location changes a little bit, the ShakeMap will change, the pager results will change. And we also have the ShakeMap go into the ground failure, and it goes into ShakeCast. As we get the estimate of the finite fault, that goes into ShakeMap, and that'll change the ShakeMap as well. And so this is all forward modeling, and the models change only when the ShakeMap changes. And what we're looking at now is adding a slightly new paradigm where we will update the pager, we'll update the ground failure estimates, and we'll update the finite fault based on a few things. One is the reports of fatalities that are coming in early, and the imagery that's available within hours to a day or two after an earthquake. And we'll then put information back into the pager system, back into our other systems, and iterate with and hopefully get to the right answer much more quickly than we would otherwise. So we're helping to constrain the prior models with information that's independent that comes in after the earthquake. We all know that for earthquakes, in this case, Pakistan in 2013, Turkey, the estimates, the reported fatalities are always going to grow with time because the early information is uncertain and only the initial victims are found. But we know the growth curves can be depicted mathematically in exponential functions. And if we can get those initial functions matched, we can estimate where they're going to end up in conjunction with what we've already done with the pager system. And so this is reported in a recent paper in Earthquake Spectra. Dr. No at Stanford, working with Kishore and colleagues in our office. And basically what we do is we get our initial estimate of pager losses. We get an estimate of we get a report of the fatalities, and we update our model based on that initial estimate. And that initial estimate happens, say, hours after an earthquake. We can then estimate what the final estimates of fatalities will be ultimately days later. And then if more fatalities are reported, we can update the prior model that's been updated from the first report and so on to get an estimate of the losses over time and improve them as we go forward. I have to skip through this fairly quickly, but the idea here is that even if our estimates of fatalities are off by 100, too low or too high, as we get reported fatalities, the estimate will get closer and closer to the ground truth with lower uncertainty as we have actual reports contribute. So if we are right on target, things won't change, but they'll get less uncertain. And if we're off, we will converge to the right solution within hours or even days of the earthquake. And we've been able to do this in test mode for a couple recent earthquakes. This is an earthquake last year in Greece. And this had 116 fatalities reported. Our initial estimates of Pager were yellow alert with this is the histogram of Pager now on its side and the alert level at the bottom. And as we got reports of fatalities come in from the field, we were able to update the loss model and ultimately get to the actual losses much more quickly through this process than we would otherwise. And so we not only get the right answer, but we get lower uncertainties, and these histograms now reflect certainty in where the ultimate losses will be. And we have other examples we can show for Croatia earthquake, where we converge to the right solution much more quickly with reported losses than we would otherwise. So these fatalities estimates, they're uncertain as well, but if you have 10 reported fatalities, then it certainly changes the probability of having 0 fatalities. And if you have many reports of fatalities early on, you know that's going to grow. And so these independent observations are very useful for updating our model. Let me skip that. The other approach that we're taking is to use imagery that's obtained from satellites to update our models as well. And the way this works is our USGS information goes to NASA, and they then can target satellites to collect imagery. And the imagery that they produce is basically the interferogram, which shows the displacement of the ground with respect to the satellite before and after the earthquake, as well as what we call the DPM, the damage proxy map, which is the change in coherency or the change in the radar signal before and after the earthquake. And that change is typically due to building damage or some kind of ground failure or some kind of change before and after the earthquake. And we're going to use those images to update our models and provide that information back out to the public. So after a major earthquake, this is the earthquake in Ridgecrest, California. The fault was it was 2 earthquakes actually, a magnitude 6.5 and 7 earthquake that followed. This is the fault, and that image of interferogram allows us to take the displacements and figure out what faults ruptured during that earthquake. That's very important, as I mentioned, for the ShakeMap. But we get another product as well, and that product is the damage proxy map, which is not the distance displacement and change in displacement to the satellite before and after the earthquake, but the change in the coherence of the satellite radar signal before and after the earthquake. And that has been shown to show changes before and after eruptions, changes before and after fires, and changes before and after flooding, as well as after earthquakes for damage. And a very clear case of that is for the Amatrice earthquake in Italy, where the interferogram showed, the damage proxy map showed very large changes in the town of Amatrice, where ultimately was reported that there were very many structures damaged. So can we use this satellite image here to help inform where the damage occurred, how much occurred, and change our prior models? So I'm going to give you an example very quickly of the Puerto Rico earthquake that we had last year, a magnitude 6.4 earthquake, a very significant earthquake in Puerto Rico. And we had relatively low estimates of landslides and liquefaction. It wasn't a very large earthquake, but there were certainly landslides and liquefaction that caused additional damage. Here's our prior model, our model of liquefaction likelihood In the area that shook the hardest, obviously has the highest probability of liquefaction. The liquefaction probability is shown to the right. These are very low probabilities over large areas. So we're not sure exactly where the liquefaction is going to occur, but we can modify these prior models based on what happened and changed in the satellite image. Here's our prior landslide model, and the landslides are likely to occur, again, in the strongest shaken area where there's steep slopes. But again, there's larger areas that are possible landslides than the actual landslides will occur ultimately. So what we do is we take this image, this is the satellite image in grayscale for the Puerto Rico earthquake. And if we zoom in on the epicentral area, there's lots of changes to the image. And the question is, as a human, can you look at this image and decide what changed? It's very difficult to do that. Obviously, there's changes a few days before an earthquake and after an earthquake. It could be change in vegetation, it could be noise, it could be liquefaction, landslides, it could be building damage. What was it? Was it even anthropogenic? Was it people moving from one parking lot and back and taking their cars out? Were there changes in the city? Was there construction going on? So we have to determine what's going on. And these things can be overlapping in the same location. You can have landslides and building damage, and landslides where changes of vegetation occurred. So it's a very challenging problem. And effectively, it's a Gaussian mixture model where you have distributions of signals that are overlapping that can be characterized as Gaussian processes and multivariate distributions. And so without getting too deep into the math, what we do is we develop a causal graph, which allows us to take the damage proxy map and attribute it to landslides or liquefaction or building damage or some combination thereof, and then have them update our model of landslides and liquefaction based on what's happened on the ground. It's a complicated model. It's something we're working on right now, but seems to be working quite well. And I don't have time to go through the exact steps here, but basically we're taking a causal graph that allows us to attribute the changes in the damage proxy map to different physical processes through the prior models that we have for liquefaction, landslide, and building damage. And with a machine learning strategy, we can use that to solve for the variables that allow us to determine not only the noise, but which of the signals are due to landslides, liquefaction, and ground failure. And very quickly, if we have a prior model of landslides and would like to update that with the damage proxy satellite map, we can then focus in on areas that are more likely to have liquefaction. And in this case, sorry, this is landslides. The blue here are actual landslides, and the posterior model is shown in red here. With liquefaction is likely to occur over a large region according to our model, but when we add the ground truth information from the satellite, we can reduce the area in our model that's likely to have liquefaction, and then it corresponds quite well with where that liquefaction actually occurred. And we can do this with buildings as well. This is our posterior building damage model and the actual building damage from these earthquakes. So as we improve this, it's conceivable that with building footprints, we would be able to determine exactly which buildings are damaged in this particular earthquake. And all together, we'll be able to separate the landslides from the building damage, from the liquefaction, from noise with this kinds of causal graph and Bayesian updating process. So I had to go through that very quickly, but effectively that's work in progress, and we're very excited about being able to use these information from the ground, whether it's actual reports of fatalities and building damage or actual reports of liquefaction and landsliding, and add that to this causal graph in the Bayesian sense to use the damage proxy map and get our prior models to be improved and ultimately get closer to ground truth. So I think I'll leave it at that because we're running out of time. But I just wanted to show you here that this is what we covered today. There's a few gaps here, but we covered a number of the USGS earthquake information systems. I'll be happy to answer questions about any of these or any of the other systems that we run. And I've left with you some papers that describe these in much more detail. And so these are all available online. And I'll give you a couple other papers that summarize the did you feel it data and a reference list here that I've mentioned today. And I think I'll leave it at that and save time for questions.
For your very informative talk on different scientific products of USGS, such as TwoPager, ShakeCast, ShakeMap, DDFilit, MS Proximate, etc., which would be very helpful not only for the researcher but also for general public. Now, may I request our session chairman, Professor J.R. Kyle, for his remarks. Over to Professor J.R. Kyle.
Yes, thank you, Shantanu. I think Professor Dr. Wald, you have really made us overwhelmed. So much information and so much educative. We have no words to thank you actually. You made it really our day today. It was a real excellent lecture and congratulations and thank you so much. I have as a layman, I have a layman question. That is your instrumental intensity that you provide is almost within short time. Now that intensity scale, how it is compatible with the say MSK scale or other scale, conventional scale? Is it compatible with these scales? And there's my one query. The other query is your ShakeMap as of today is mainly based on that you do feel it that information and by radio communication, as you say. It is not instrumentally recorded setting data. It is just on public information on radio communication. So these two queries.
Yeah, so very, very important questions. The first question is our comparison of the recorded acceleration, velocity, and spectral acceleration with intensity was done with the modified Mercalli scale primarily. Now, Roger Musson has spent a lot of time comparing intensity scales, and he has some very good comparisons. And effectively, MMI, modified Mercalli scale, can be considered equivalent to EMS 98 under most circumstances. And so we're very comfortable with replacing EMS 98 and modified Mercalli intensity with our conversion equations. When you get to MSK and ESC in Italy, there's slight differences, and that gets to be a little bit more complicated. But the Italians, when they run ShakeMap, they use a slightly different intensity conversion for that reason. So it's not ideal, and converting from ground motions to intensity itself is inherently uncertain. And then if you have to convert to a slightly different scale, that adds additional uncertainty. Now, your second question about your typical ShakeMap is very not typical. If there's a ShakeMap in Los Angeles, California, there are hundreds of seismic instruments that go in the ground. There's also thousands of Did You Feel It reports, but the ShakeMap weights the seismic instruments more than the Did You Feel It data. The Did You Feel It data is reported and it has its own uncertainty. Seismic stations at the location of the station has no uncertainty, right? It's exactly the acceleration that was recorded. So one of the mathematical challenges in the ShakeMap system is to combine the intensity from the seismic instrument with the intensity from the reported intensity, and do that appropriately so that the more accurate one reflects the shaking. And the way that works is if you're an engineer and you're interested in the acceleration of the ground, the seismic instrument is going to be weighted much more. If you're interested in the intensity, what was experienced, the Did You Feel It data is actually the native answer. It is more accurate than, so if you wanted to know if the chimney fell, somebody might observe a chimney. If you know the acceleration, the chances of the chimney falling is a probabilistic problem. So, it's interesting because Did You Feel It is effectively ground truth for intensity, and the seismic instrument is ground truth for the acceleration. So ShakeMap treats those native metrics appropriately. And as you mentioned, if I go to other parts of the United States where there are very few seismic instruments, the ShakeMap will be heavily dominated by the predicted shaking and the did you feel it data. So our preference would be to have seismic stations everywhere.
Yes, that's what you said, yes.
Of course, we don't have that. We don't have that, so we make do with the reported intensities.
Yes, thank you so much. Thank you. Wonderful, wonderful lecture. Thank you.
Thank you, sir. Thank you, sir. Now we can have some questions from our attendees. Now about the procedure.
Thank you, sir. Thank you, Dr. Wald, for such an informative lecture. We have a lot of questions in the Q&A section from the participants across the globe. With your permission, sir, I'm going to read out a few of the questions. So the first question is, how can we get USGS catalog having same scale of magnitude as in ISC catalog?
I'm sorry, you're gonna have to read that last part again. The USGS catalog, that part?
How can we get USGS catalog having same scale of magnitude as in ISC catalog?
I'm not certain of the technical question there, but the USGS has, when you go to the USGS, what we call a COMCAT, Comprehensive Catalog, one can search for earthquakes based on space and time, and you can look based on other catalogs. We have the ISC catalog, we have the ISC GEM catalog, and one can relate the two catalogs by their event ID. And there's tools in the search engine that allow one to replace one catalog for the other. So I would suggest going into the search engine on the USGS webpage and looking very carefully about the search options. If there's any questions about that, please send me an email, and I'm wald@usgs.gov. And by the way, if there's questions that I don't get to answer, if you can send those to me, I'll be glad to answer those at a later time.
Sure, sir. We are going to email you the question here, sir. The second question is, while estimating the intensity of a historical earthquake, do you take into account the information acquired through the paleoseismic studies? How useful the paleoseismic data in estimating the modern day probable intensity in case of recurrence of a similar event?
Yeah, going back in time is challenging, and the problem is that construction practices change over time, and so it's a little difficult to assign intensities in the modern era in a comparable way to intensities 100 years ago. If the people doing the assignment keep that in mind, then they can look at buildings that were available at the time of the earthquake 100 years ago and compare those to, the vulnerability that we would expect with today's intensity scales. So I would say that it's possible to do this, but it adds uncertainty to the intensity assignments, and that's something that one has to keep in mind. In the past, only information about what was damaged was saved, not information about what wasn't damaged. And in modern intensity scales, what we look at in EMS 98, we look at the ratio of damage to undamaged structures to get a very accurate assignment. And that can't be done for historical earthquakes.
Okay, thank you, sir. The next question is, what happened to the last 2021 South Sandwich Island earthquake when the magnitude of 8.1 event was hidden after the magnitude 7.5 earthquake? What can we learn from this event for a near real-time seismological observations?
I'm sorry, what was the event again? 7.5 and 8.1 South Sandwich Islands?
South Sandwich Island earthquakes.
Yeah, well, those event sequences are always a challenge. Of course, those were fairly remote. And my expertise is not in triggering and subsequent sequences of earthquakes, but I would say that one of the challenges is to be aware of the aftershocks and the evolution of aftershocks for earthquakes to see if there's a pattern that represents existing faults or could rupture adjacent segments. And that's something we're always concerned about when the earthquakes occur on land, where we know where the faults are, and the migration of seismicity is going towards those other faults. But that's not my specialty, so I'll avoid that one.
The next question is, how important is the availability of a near real-time finite fault slip model for generating the ShakeMap?
Yeah, that's a real challenge. It turns out there's some earthquakes where it doesn't matter at all. If you have hundreds of seismic instruments in the ground, the ShakeMap will be driven by the actual shaking in the ground, and where the fault occurs will only change your estimates of the shaking. So the more instruments you have, the less important the finite fault is. Now, if you move to an area where you're on land and there are very few seismic stations, the pattern of shaking will be driven by the finite fault, but you won't have any constraints on that finite fault. And so there, it's very important to get that fault location. If there's an offshore earthquake, a subduction earthquake, say a magnitude 8 earthquake off, say, South America, the location of the fault isn't as important as it would be if it was on land, because its distance to the shore and to the on-land areas is greater, and the uncertainty in the location of the source is not as important. So it depends on the earthquake, it depends on the seismic station coverage, and it depends on how deep and how far away the earthquake is, how important the finite fault will be.
Okay. The next question is, how the pager takes the structural characteristics into account. Example, some structures might have seismic isolation system or dampers, etc. So how these features can be considered?
Yeah, so here's where the great uncertainty in the pager estimates come from. So the current operational system is empirical. It is based on what's happened to that population in the same region in historical earthquakes. So the assumption there is that the building characteristics, the overall building characteristics haven't changed. Obviously, in different cities around the world, buildings do improve with time. In some cases, in other cases, they don't. And we do not have a very detailed inventory of the buildings. So we estimate the aggregate losses of all the buildings based on recent earthquakes. So if you go to a city, say in China, that has completely rebuilt and has all structurally sound buildings, we will have to change the model to accommodate that. And the reality, of course, is that cities don't change very much over time. Even if you take 10% of the buildings and make them much better, the losses will occur from the 90% of the buildings that haven't been improved. And so that tends to be pretty constant over time, unfortunately, around the world.
Sure, sir.
I think we can start.
Make it the last question.
Sure, sir.
Yeah, that's it.
Quite
Yes, sir. Yes, sir. So the last question will be, how the economic fatality is calculated? Which factor are considering for this estimation?
The very beginning of that question again, the economic, is that what it was?
Economic fatality is calculated.
Yes. So the economic losses are calculated also empirically based on the losses that were reported from previous earthquakes. Now, one has to appreciate that economic losses themselves are fairly uncertain estimates of what happened. It's always uncertain what the true economic losses were. So we take the reported economic losses, and in a very similar way to what we've done with the fatality estimates, we look at past earthquakes and we look at the population exposure per shaking level. And rather than looking at a fragility curve that tells us the fatality rate, we look at the GDP per capita, and we calibrate that against the shaking level and the economic losses for past earthquakes. So if we have an earthquake like the Northridge, California earthquake, there were $40 billion worth of losses, and we know the population exposed, we know the GDP per capita in Los Angeles, and we know the shaking level of that population. We can estimate for a new earthquake what with what a different shaking pattern would do in terms of economic losses. Again, it's an uncertain process, and in order to do better, one would have to know where every building is, how much every building costs, and how fragile each structure is to shaking, which is in this current day and age impossible. So we do this as a calibrated empirical approach against previous earthquakes in the region.
Thank you, David, and thank you, Prasithya. Now I think we have the end of the session. Now over to Mr. Navajyoti Mondia for both of things. Over to Navajyoti.
Thank you, sir. A very good evening from India. As today's event has come to an end, it is my pleasure to deliver the vote of thanks to one and all. At the very outset, I, on behalf of CSIR NIS Jorhat and organizing committee of IBWGST 2021, would like to thank Dr. David J. Wald of USGS USA for readily accepting our invitation and delivering today's talk on an overview of USGS near real-time earthquake information product. Thank you, Dr. Wald, for sharing your experience with us and enlightening us with significant information about the real-time seismic data products of USGS. Once again, a hearty thank you. I further would like to take this opportunity to venerate our Honorable Director, Dr. G. Narahari Sastry sir of CSIR NIS Jorhat, for his immense concern and suggestions to successfully organize the live session meets. Sir, hearty regards, and we are sincerely thankful to you. Our heartfelt thanks goes to esteemed international advisor of this workshop, Dr. Andrew J. Michael from USGS USA, and session advisor, Professor Daping Zhao from Tohoku University, Japan, for his constant vision and support for the event to be a grand success. I would also like to thank the session chairperson, Professor J.R. Kyle sir, former Deputy Director General of GSIR, GovTop India, and co-chairperson Dr. Saurabh Burwa, Chief Scientist CSIR NIST, for their meticulous support and guidance towards the event. Once again, I take this opportunity to thank Dr. Santanu Burwa, convener IBWGST 2021, for his energetic dedication towards this international live session meets. We once again sincerely thank him a lot for rendering this opportunity to unite eminent seismologists, researchers, and personalities from different parts of the globe in a single platform. Last but not the least, I would like to thank all the participants for their active participation in today's event, without which this event would not have been a success. We are also looking forward to see you all for tomorrow's session, sharply at 9:30 a.m. Indian Standard Time. Our speaker for tomorrow's session is Professor Dr. Alan Kafka from Boston College, USA. He will deliver his talk on his reflection of past 2 decades of teaching on geoscience and public policy. With this, I conclude with hearty regards and anticipation. Namaste, and thank you all for your kind presence. Thank you, sir.
Thank you.